So if we look at this graph right here, the definition said to be an odd function, it had to be reflected over the y and x function axis. So if you notice this piece right here, we reflected over this side and then reflected over the x-axis, we get the same graph. Also, if you notice that its coordinates, both the x and the y are opposite points. That's a reflection over the x and the y. So that means that this is an odd function. And that's how we figure out if something's odd graphically. Algebraically, we have to look at our function. So the definition says if we substitute in negative x for our function, wherever we see an x, and we simplify it, if you notice, we could factor out an x from both of these terms, and now we have negative f times the function. So if we could factor out a negative, then we have an odd function, which means that the signs of each of these terms has changed. So if you look for the previous step, before we factor out our negative, the signs changed between the x to the fifth and negative x to the fifth. Now, originally we had 3x cubed, and then it became positive 3x cubed. If each term changes sign, that means we can factor something out and we'll get our original function, which is this one, times a negative. You guys worked, and we talked about this in class about what do we have to do to get an even function and a neither function. What would we have to change on this function for that to happen? We agreed that the exponents for both of these would have to be even exponents, like squared or the fourth power or the sixth power, because if anything that is squared or to the even power, it doesn't change the sign, it'll still stay positive. And for neither, we said that we had to change the first one to even and the second one to odd, because then it would be neither odd nor even function, because for even function, we have to have the same function, and for an odd function, we have to be able to factor a negative from each term. And in this one, we wouldn't be able to do that. We would not get the original function. For this problem, we graphed it, and if you could see, we got this curve, and visually, graphically, you can really tell that it's not reflected over the x-axis or the y-axis. So there's no reflection. That means it's neither. So this is graphically. Algebraically, if we substitute the negative x into our original equation, we get a negative x there and we get a negative in here. We cannot factor a negative out from a square root. So that means that it's neither, since when we substitute the negative x into our original equation, we don't get our original function, so it is not even. And also, if we substitute our negative x into our function, we can't factor out a negative from this term, so it's also not odd. And you guys also worked on this in class during our discussion, and we agreed that the only way this could happen is if this is even and this is even, you could get an even function, because this will not change it, and this will give us the original positive function. And then for the odd function, we discussed that we would need the first one to be odd and this one to be even, since we cannot factor anything from the square root. And since this together is being multiplied, this is basically a monomial. And if you change that, then you're technically just changing the sign of the first one, which would be the opposite. And then we got our g of x equals x plus 4, and we graphed it, and we had an absolute value that was shifted to the left 4 units. And if you see graphically, it is not reflected over the y-axis or the x-axis, so it is neither. Algebraically, again, we substituted in and we cannot factor anything from an absolute value. So algebraically, we have proved that it's neither, since when we substitute g of negative x, it does not equal g of x, which is would be an even function. And when we substitute the negative x, we don't get a negative g of x, which would be an odd function. So this is for A, this is for B.